Hi, I'm Cardin Baylor, and we'll be going over detecting fraud in peer-to-peer networks today using Aura Graph Analytics. To kind of set the stage for the problem, fraud in peer-to-peer networks is increasingly becoming a larger problem. In fact, 8% of banking customers reported being the victims of a peer-to-peer fraud scam in the past year. The average loss to one of these peer-to-peer scams was $176, and that was all the way back in 2022. That volume is probably way higher now, considering that there is $2.3 trillion expected in transaction volumes in these peer-to-peer networks. Uh, so how are we going to take a look at that with Aura Graph Analytics? So we're going to be starting with anonymized financial transaction data, and we will detect communities, identify important financial nodes, and resolve entities. And we're going to do all of that quicker than you can and with better results than you would with traditional analytics. So this will be pretty simple. We're going to load some data into a projection. We're going to run some algorithms, and we're going to write the results back to a graph. And this is all available in a pay-as-you-go serverless offering that runs up to twice as fast as open source competitors. So just a little quick insight into the architecture in which we're working. We're going to be using an AuraDB as our starting point. We'll then project a graph into memory on the serverless option. So it won't be, we're separating the compute and the storage here. We're going to be running our algorithms, and then we're going to be writing back to AuraDB. So we're going to be bringing the compute to the storage here rather than having the compute and storage be together. So storage is separate from compute. But before we do that, I want to briefly talk about one of the key algorithms we're going to be using, which is weakly connected components. So consider the below graph. We have pretty intuitively two natural groupings here. And I actually already color coded them for your convenience. So if you can't guess already, we've got this red group here and this blue group here. So how do weakly connected components work? If we wanted to do a simple breadth first search to see what was happening without the directions, we would then find that there's two groups. So that's literally all we're doing here is we're saying, okay, for weakly connected components, don't consider the direction of the edges, and if you can, trace your finger from one node to the other following these lines, then you have a weakly connected component here, and then you have a different one here. There's also something called strongly connected components. This just means you have to be able to reach each node using like the direction of the relationships. So you actually have to be able to traverse it, accounting for the direction. But with weakly connected components, you don't. So in the fraud example, we're going to be using, essentially what we're going to do is we're going to have some nodes that are already labeled as fraudulent, and we're going to try and find all the other nodes that are connected with them. Just to briefly give you a little bit of a rundown of what we're going to be doing, we're going to be drawing new connections, new relationships between nodes based if they have a shared ID or if they've shared a credit card in the past. And then we're going to see if we can find newly identified nodes that are fraudulent. So with that, we're going to jump into the notebook. So the first thing you're going to have to do is you're going to have to install the Graph Data Science package. This is all going to be in a Colab notebook. You're going to have to install Neo4j one, and you're going to take your client ID and secret from AuraDB as well as the tenant from your Aura account rather than AuraDB, and then you're going to give your AuraDB login information here. So next, you're going to create a session using GDS sessions here. You're going to give it a name, and you create an estimate of how large it is and include some potential things. And this will just kind of right size the size of your the session that you're creating. Make sure it's not too big, but also big enough to handle your workload. So then you're going to do sessions, get or create, and create a sessions object. Once you create this session, the billing will start. So we're going to create that. And the first thing we're going to do is we're going to run a cipher against our notebook to just get an idea of what's in it. So we have users, we have these flagged users, these fraud risk users, and we're going to be using that kind of as our starting point. And we have some relationships, and then we're going to get an idea of the size of things here. So you have, 33,000 people who are not fraudulent, most likely, and 241 who are. We're then going to create a new node label called flagged user, which has 241. So these are our kind of known fraudsters. We're then going to create new relationships. First, we're going to show ones that have a shared card. Then we're going to create one that has a shared ID. And that creates 6,200 and 5,300 new relationships, respectively. So next we're going to create a new projection. All we're going to include in our projection is those individuals just all the individuals rather, plus their relationships if they have a shared ID or a shared card, and if they don't have either, they'll just exist as singleton communities, so just like individual nodes. So now we have our projection. So at this point, we have created our projection, and next we're going to run algorithms against it. So the first one we're going to run is weakly connected components. Again, what we're going to be doing is seeing, if we look over here, if this user had a fraud flag and he shares a credit card with this user, or he shares an ID with this user, all of these are now going to be in the same community. They're going to be in a potentially fraudulent community. So all of these individuals are suspect for fraud, and this is a form of entity resolution based on shared credit card or shared ID to see if they are potentially the same fraudulent user acting maliciously. So we do that, and we find, if we're looking at the count of individuals who are in a weakly connected component that has a flag, we find there are 452 total fraud risk accounts. We already had found 241, so we identified 211 new fraud risk user accounts. So next, we're just going to break down the number of components. So we have 24,000 singleton communities that aren't sharing a credit card or an ID with anybody, and 118 of them have fraud. We have 3,000 ones with 2 components in them, 400 with 3, and then only one with over 50, and that doesn't have any fraud in it. And then 15 is between 11 and 50 components within it. So, like I said, this helped us identify 211 new fraud risk accounts, and we can see that around 65% of the money going to or from previously flagged accounts and other users can be attributed to these newly identified risk accounts. Additionally, these 211 accounts represent less than 1% of the total users in the sample, but 13% of the total peer-to-peer transaction volume, meaning that these users are highly influential and highly sending a lot of money through the system. So it's good that we've caught them, because we've caught probably around an additional 13% of fraud that we otherwise wouldn't have had. So after that, we end our session and the billing stops, and we can go on to our next bits. The next things you'd probably want to do is kind of more closely examine those users that are in their potentially fraudulent accounts, and see if they are in fact fraudulent, or if they're victims of fraud, or what is happening. And that is how you can do entity resolution in a fraud context. And yeah, that's it for the fraud and weakly connected components and Aura Graph Analytics.